The Python language was first created in about 1990 by a Dutch guy named Guido van Rossum, who is still pretty much the guy in charge of the language, but formal responsibility has been handed over to an organization called the Python Software Foundation. The Python Software Foundation effectively decides what's proper Python and what isn't. There are a few different implementations of Python, but by far the most popular is the one created by the Python Software Foundation itself, called CPython. So called because the CPython interpreter is itself written in C. When people talk about Python, they usually have in mind CPython. The other implementations like Jython aren't used nearly as much. Jython, as the name hints at, is a Python interpreter written in Java. IronPython is an implementation written for the .NET platform, and PyPy, very interestingly, is an implementation of Python written in Python itself. Just to be clear on that, it's a Python interpreter written as a Python program. One reason these three other implementations aren't used nearly as much as CPython is because they're less mature. In fact, they all lag behind in features. Jython, for example, doesn't include any of the features that have been added to CPython in about the last 4 years. A couple years ago, Python started a big transition from version 2 to version 3. And the big deal about Python 3 is that it not only added new features to the language, it actually changed some features of the existing language. So this means that code written for Python 2 in most cases won't run under Python 3, and vice versa. So code written for Python 3 won't run with a Python 2 interpreter either. Because of these changes, it's going to take a long time for code written in Python 2 to be updated to run for Python 3, and for some programs that in fact will never happen. So this means that the Python Software Foundation can't immediately stop development for Python 2. They have to still keep releasing new versions of Python 2. So it's almost as if Python 3 and Python 2 are actually separate languages. So far, the transition to Python 3 has been really quite slow. It's been almost 3 years now, and it'll easily take another 3 years before most new code written in Python is written in Python 3 rather than Python 2. As it stands, many people today still choose to start new projects in Python 2 rather than Python 3 because they need to use some piece of code which is written in Python 2 and won't work with Python 3. Despite all that, we're going to be covering Python 3, because I think Python 3, for one, is going to be the future eventually, and also, though it's by no means a radically different language, the changes are mainly quite small, the changes generally are for the best and make things simpler. So that's why I prefer to teach it. If at any point the need arises for you to work with Python 2, it shouldn't be hard at all for you to pick up on the differences after you've learned Python 3. So, what kind of language is Python? Well, it's nothing too surprising by now. It's an imperative language and it's dynamic, just like JavaScript and just like Pidgin. And in fact, semantically, it's very, very similar to JavaScript and also Perl and Ruby. The one big difference compared to JavaScript is that Python is a more explicitly object-oriented language, because Python has a formal mechanism for classes. To be clear, nothing in Python forces you to create your own classes, so you can write all of your code in a procedural style, but typically, most Python code is written in a mix of the procedural and object-oriented styles. So, jumping in, here's a snippet of JavaScript code, and here's the equivalent in Python. The first thing to note here at the top, comments in Python begin with a single hash character rather than 2 slashes as in JavaScript. And then in the next line, a function is defined starting with the reserved word def, short for define, rather than the word function. And the two other things to note about this function definition is that the header ends with a colon, and then the body of the function is written indented underneath, just like in Pidgin. We don't use curly braces to denote bodies, we just use indentation. And you can see the same thing in the if. The if header ends with a colon, and then its body is indented underneath the if. So Python syntax is indentation sensitive like Pidgin, not freeform like JavaScript, and as we'll see later, Java and C and most other languages have freeform syntax. In fact, Python is really the only major language which is indentation sensitive. The last couple differences to note here is that first, the condition in the if, x less than 3, doesn't require parentheses around it. And last thing to note here, in Python we can create local variables just by virtue of assigning to them. So here x, we don't have to declare that that's a local variable, it's just implicitly a local variable. As we'll see later, this actually creates a little bit of an issue when you nest functions inside others, just like you can do in JavaScript. Because that means in Python then, we have to, in some cases, explicitly denote that a variable is not local to that function, even though we are assigning to it in that function. Usually though, this isn't a problem, so it's just a nice little stylistic allowance that we don't have to declare our local variables. So, in summary here, you can see that in some ways Python is more like Pidgin, but in other ways it's more like JavaScript. Like in Pidgin, comments begin with a hash character, code is indentation sensitive, statements don't have to end with semicolons, and local variables and functions are implicitly created by assignment, but unlike Pidgin and like JavaScript, expressions in Python use infix notation rather than prefix notation. The basic data types in Python should be nothing surprising. They're basically the same things we saw in Pidgin and JavaScript. The only thing to note is that Python uses the terms lists and dictionaries, where JavaScript uses the terms arrays and objects, and what JavaScript and Pidgin call null in Python is called none. And yes, it's written always with a capital N, which is actually kind of aggravating because that makes it harder to type. Every data type in Python is a class, and for every class there is an actual object representing that class. So here in the diagram, each of these represents an object, which is a class. Bool here is the Boolean class, str is a string class, int is the integer class for integer numbers, list for lists, dict for dictionaries, and function obviously for functions. And like in a lot of object-oriented languages, the classes in Python are arranged into a hierarchy with a class called object at the top. So the arrows are indicating here that, for example, the bool class is a direct child of the object class. When you create your own classes, they will by default directly inherit from object. So the class Natalie here is a child of the object class. You may, however, specify that your new class inherits from some other class. Say here Aaron inherits directly from Natalie, and Roy is inheriting directly from the int class. Notice though that for any class you create, object is going to be the ultimate ancestor. This makes sense though, of course, because anything you create is a kind of object. Keep in mind that the idea of a class is we can produce from it other objects which are instances of that class. And in fact, every object in Python is an instance of some class. So what about class objects themselves? Well, the answer is that they themselves are instances of the type class. I suppose Python could have called it the class, but they decided that was confusing. Actually in Java, that's what they chose to call it. In Java there's a class, but in Python there is a type class. So what's really confusing here is the relationship between type and the object class and the other classes. As the arrow from type to object here is indicating, type is a direct child of the object class, but that's just the inheritance relationship between these classes. Type is a child of object, but very strangely, the object class is itself an instance of the type class, and also it's an instance of itself. So think about this. The object class object itself is an instance of the type class, because the object class is a class. However, the object class is also an object, so it is also an instance of itself. And then the converse is true of the type class. The type class is an object, so it's an instance of the object class, but it's also a class, so it's an instance of itself. So let me just repeat that. Object and type are instances of each other and also instances of themselves. So object and type have this weird incestuous relationship. The same is actually true for every class object. Every class object is an instance of both the type class and the object class, because they are both classes and they are objects. But for every object which is not a class, that object is just an instance of its class, and then indirectly they are instances of that class's ancestors. So, for example, if we create a function, that function object is an instance of the function class, and in turn it is also an instance of the object class. And say if we create an Aaron instance, that object is an instance of the Aaron class, and in turn an instance of the Natalie class and the object class. To create an instance from a class in Python, we invoke it like a function. So here, for example, assuming Natalie is a reference to the Natalie class, then if we invoke it like a function, this expression returns a new Natalie instance. Now, we can do this with any class, but of course for some of the built-in classes, like say function, we wouldn't create functions this way. To create a function object, we use a def statement. For any class, though, which isn't built into the language, this is what we use. Most objects in Python have what in JavaScript we call properties, but Python calls attributes. You should recall from JavaScript that when you look up a property on an object, if the object itself does not have a property of that name, JavaScript will follow this special link from that object to another object, and it'll keep looking up the chain until it finds a property of that name. A similar thing happens in Python, except the search follows the chain of inheritance through the classes. So here, for example, we have an Aaron object, which is an instance of the Aaron class, which itself inherits from Natalie, which in turn inherits from object. If we try to get an attribute named foo from the Aaron object, Python first looks in the Aaron object, and if there is no such attribute of that name, Python then looks in Aaron. Failing there, it then looks in Natalie, and failing there, it looks in object. And if object doesn't have any attribute of that name, Python will throw an exception. Things work slightly differently when we look up an attribute on a class object. If we look up an attribute foo on the Aaron class here, Python first, of course, looks in that Aaron class, and failing to find it there, it then looks in the Natalie class, and then it looks in the object class. But then, unlike with an attribute search on a non-class object, Python will look in the type class. This makes sense because Aaron, a class object, should have all the things which type has. And so when we look up attributes on Aaron, we expect to find the stuff which is in the type class. This attribute search behavior is the essence of the relationship between instances in their class and classes and their parents. When I create a class Aaron which inherits from Natalie, the Aaron class and the Natalie class each have their own independent set of attributes, but when I look up something on the Aaron class or in an Aaron object, the attribute search will reach Natalie. So if the Natalie class, say, has a method named foo, but the Aaron class does not, invoking a method foo on an Aaron instance will invoke that method foo in the Natalie class. Likewise, if the Aaron class has an attribute bar, which is assigned a function, then if we invoke a method bar on an Aaron instance, that Aaron instance doesn't have to have its own function bar. When the attribute search for bar doesn't find anything in the Aaron instance itself, it'll look to the type, it'll look to the Aaron class. For fields, though, it's a different story. When we create instances of class, each instance should have its own fields. So say, if Aaron objects are supposed to have a field named X, then every Aaron instance should have its own attribute named X. Now, it's not the case that every object in Python has attributes which we can assign to and retrieve. First off, the attributes of the built-in classes, such as object and type, can't be modified. If you started messing with these classes, you'd very likely break the whole language, so Python simply doesn't let you do it. It's also the case that for some of the built-in types, their instances don't have any attributes at all. So, for example, while the string class and the number class and the list class all have attributes, the instances produced from those classes do not. This effectively means we can never assign to an attribute of these instances because they don't have any attributes, but it doesn't mean we can't look up attributes on these instances, because when we do so, the search for that attribute will of course not find the attribute in the instance itself, but it will look for the attribute according to the normal search rules. It'll look in the class and then up the chain of inheritance. So here, for example, the string literal hello, that's a string instance which we assign to the variable x, and then if we write x.foo equals 3, that's attempting to assign 3 to an attribute foo of that string instance, and that's not legal, so this will throw an exception. But it does make sense to write x.upper because upper is an attribute in the string class. So x.upper here will retrieve the value of that attribute in the string class. Recall that in JavaScript, writing x.foo is basically just a shorthand syntax for writing x and then in square brackets a string foo. This is not the case in Python. In Python, dot is the only way to access attributes, and the square bracket operator is a totally different operation. Square brackets are used to retrieve and set the key value pairs of dictionary objects. A dictionary in Python is an instance of the dict class, and when we look up values in a dictionary, there is no concept of a search order. The search is done just in that dictionary itself, not in any other object. So the intention in Python is that you don't just use any object with attributes as a grab bag in which to stuff a bunch of key value pairs. For that purpose, you're supposed to use a dictionary. It's really kind of weird how JavaScript does it, where these objects are used both as collections and then also to represent data types organized into a hierarchy of inheritance. It's clever how they only have the one simple mechanism to cover both those bases, but it's just weird. To make what's going on in Python clearer, let's look at dictionaries. First off, to create a dictionary, we can simply invoke the dictionary class called dict. This returns a new empty dictionary. More commonly, however, we create dictionaries with curly braces, just like we create objects in JavaScript. So here, this empty pair of curly braces, that returns a new empty dictionary, and then the second pair of curly braces has two key value pairs. The first with the key string of foo and the value 3, the second with the key number 4 and the value 12. Two differences from JavaScript to note here. The first is that the key string foo must be written explicitly as a string. We can't just leave off the quote marks as we can in JavaScript. If we were to just write the identifier foo here, that would be the variable foo. So the key value pair here would be the value 3 with the key of whatever is in the variable foo when this dictionary was created. The other difference from JavaScript is that Python dictionaries can have keys which aren't strings. So whereas in JavaScript writing 4:12 would represent a key value pair of the string with just the character 4, here in Python this is a key which is actually the number value 4. So as mentioned, to retrieve the values from a dictionary or to set key value pairs, we use the subscript operator, the square brackets. Here we're creating a dictionary with 3 key value pairs and assigning it to x, and then in the next line the expression x subscript 56 retrieves the value of the key 56, which here is 11. And then in the next line, when we write x subscript string orange and assign it 14, that is assigning a new key value pair with the key of the string orange and the value 14. And then in the last line, we're assigning another key value pair. This time the key is -30, and the value is a new empty dictionary. So to reiterate, the subscript operator, the square brackets, is used just to set and retrieve key value pairs from dictionaries. It is not used to retrieve or set attributes of objects. However, the subscript operator is also used with lists to get and set the items of that list. So very briefly, we can create a new list object by invoking the list class that returns a new empty list, or more commonly we just used square brackets just like we did in JavaScript to create what it calls arrays. Here we are assigning the variable x a new list with 3 items, first 67, then none, and then a string George Washington. And in the next line, the expression x subscript 0, that returns the first item, 67 in this case, and then if we write x subscript 2 equals the string hello, that is reassigning the third slot in the list. So previously it had the string George Washington, now it has the string hello. Unlike with JavaScript arrays, we can't assign out of bounds on a Python list. So here when we write x subscript 3 equals 9, that's going to trigger an exception because index 3 would be the 4th item in this list. This list we created only has 3 items. If we want to add a 4th thing to this list, we have to first expand the list, and there are methods in the list class for doing that, which we won't cover here. We'll get to that stuff in the supplementary material. Let's look now at how method calls work in Python. The goal here is when we invoke a method, say x.foo, x somehow has to be passed as an argument to the method. So assume we have some class called Aaron, and that class has a function in an attribute named foo. If we then create an Aaron instance and assign it to a variable x, and write x.foo, that expression x.foo is looking for the attribute foo on the object of x, which here is an Aaron instance, and what it returns is not the function found in the class Aaron, but it takes that function and it wraps it in another kind of object called a method, and it returns that method bound to that object in x. This is a special behavior only for functions. In the class Aaron, the methods are expressed as just attributes which are functions, but then when we look them up via instances of that class, what we get back are method objects. What a method object consists of is simply a reference to the function and a reference to the instance, here x. When a method object is invoked, it invokes its function and passes on any of the arguments that were supplied, but it inserts the instance as the first argument. So here, when we invoke the method object with the arguments 3 and 5, that invokes the function from foo, but with x as the first argument. So the arguments to the function are x, 3, and 5. What methods are is really just an elaborate mechanism to somehow get that object before the dot, in this case x, passed as the first argument. When we create a class in Python, the convention is that any of the functions we give it for methods, the first parameter by convention expects to receive the instance. So when you see in code what looks like a method call, say x.foo with the arguments 3 and 5, what's happening is the expression x.foo first returns a method object, that method object wraps x and the function, and then the invocation of the method object causes the function to get called, with x as the first argument, followed by all the remaining arguments here, 3 and 5. Now, it turns out that most of the operators in Python are really method calls in disguise. For example, x plus y, Python implicitly translates that into an invocation of the method add with 2 underscores on both sides. And the first operand of the plus sign becomes the instance of this method call, and the second operand gets passed into the method. So x plus y becomes x dot underscore underscore add underscore underscore with the argument y. And it's the same idea for the other arithmetic operators. Subtraction becomes sub, multiplication becomes mul, division becomes div. And the reason for the underscores is that Python has a convention whereby any attribute name which is generally not meant to be accessed directly, such names by convention start and end with 2 underscores. So the intention generally is that the add method here is not invoked directly, rather we invoke it by using the plus sign operator. Now, usually when you use arithmetic operators, you use them on numbers. So imagine here that x is a number, it's an integer. And so the method add here is being invoked on an instance of the integer type, int. If you look in the int class, you will find these attributes. You will find underscore underscore add underscore underscore, you'll find sub, you'll find mul, you'll find div. It's the functions of these attributes in the int class which get invoked when we use the arithmetic operators on integers. Now, you're probably wondering 2 things. First of all, if the addition operator ultimately invokes a function, what happens in that function to do the addition? Because that function just can't use the addition operator, because the addition operator would call that function again. It doesn't make any sense. That would be circular. So the answer here is that the integer class has functions which are specially created by the interpreter. They're not regular Python functions. They're what are called built-in functions. They don't contain Python code, obviously. In the CPython implementation, for example, these functions likely contain C code. So that explains that mystery. The other very puzzling part about these operator methods is why have them at all? Why not just define, say, the addition operator, the plus sign, to directly do addition? That's how it's done, say, in JavaScript, so why doesn't Python do the same? Well, the idea is that if operators really invoke methods, that means when you create your own classes, you can define methods of these names, like say add, and thereby give instances of your class defined behavior with the standard operators. So if our class Aaron has a function in its attribute underscore underscore add underscore underscore, and that function takes 2 arguments, then that gives Aaron instances defined behavior with the plus sign operator. So if you write x plus y, where x is an Aaron object, that'll work. It'll invoke the add method of the Aaron class. Now the question still is, what the hell really is the point of this? Why is it so great to have your own classes work with the standard operators? I, for one, think it's really quite pointless. It's really just making a stylistic allowance, whereby in certain circumstances you may make your own data types work with the standard operators. And for whatever reason, you don't like the idea of giving that operation a standard attribute name and invoking it like any other method. A better argument for this arrangement, though, is that it gives the language pervasive polymorphism. If method calls can be polymorphic, they can change based upon the arguments and the type of the object, well then why shouldn't operators also be polymorphic? Whether or not you object to this feature, it does exist, and it applies not just to these arithmetic operators, it applies actually to most operators, including the subscript operator on dictionaries and lists we saw earlier. So when you get or set items, say, from a dictionary, those are really method calls in disguise. They are called getItem and setItem respectively, both surrounded in double underscores. But for now, we won't enumerate all of the different operator methods. We'll save that for the supplementary material. Now, actually, there is one last thing we need to say about these operator methods, and that is that the attribute search behavior gets slightly modified when using these operators. For example, say again we have a class Aaron and we have an instance of Aaron A. And then we do an attribute lookup for __add __. Well, because we're looking up the operator method explicitly by name, this is done like a regular attribute search. First, Python looks in the Aaron instance object itself, then it looks in the class Aaron, then in its parent, all the way up to object. However, when we use one of the operators which implicitly translates into a method call, the attribute search behavior slightly changes. So here, when we write a plus b, that's implicitly invoking a dot __add __ with an argument of b. So the attribute search for that __add __, the search doesn't start, as usual, in the Aaron instance itself, rather it starts directly on the class. So the special rule for these operator methods is when invoked via the operator, the attribute search skips the instance itself. Now, 99 times out of 100 when you invoke a method, it doesn't matter if you skip the instance itself because methods are generally attached to the classes, not the instances. In the case of these operators, we know that the attribute search is looking for a method, not any other kind of attribute, so it's safe for Python to skip the instance. That's one reason Python does it. There's a small little efficiency gain in that it doesn't have to search first in the instance. The real reason for this rule, though, is that when we use an operator on a class object itself, we don't want the operator method to be found in that class itself. So for example, if Aaron itself had a method called __add __, and we invoked Aaron with the addition operator, don't ask me why you would do this with a class, but if you did, you wouldn't want it to be found in Aaron itself, because when Aaron defines an add method, that's for instances of Aaron, not for the class Aaron itself. Now, I will say that defining behavior for standard operators with class instances is already a questionable thing to do, but it'd be really weird to do the same for classes themselves. However, there are a few operator methods defined in the type class, such that there are some operators that work with classes as part of the standard behavior. We won't discuss that stuff now, though. We'll save it for the supplementary material. Finally, let's look at how to actually create your own classes. Classes in Python are created with class statements. Class statements superficially look a bit like function definitions. Instead of def, you have the reserved word class, and then you put the name to which the newly created class object will be assigned. Here, the name is Jack. And then following that in parentheses, rather than an argument list, we put simply an expression which returns a class. This becomes the parent of the new class we are creating. So here in the parentheses, we have an expression of a variable Kate, presumably referring to the Kate class. And then after the parentheses, the header ends with a colon, and what follows is a body of code. This body of code gets executed once when the class is created. So be very clear on that. When you define a function, the body of the function is not executed when the function is created. It's only executed when the function is invoked, and that may happen many times. Here, the body of the class executes when the class object itself is created, and that only happens the time the class statement itself executes. Now, the body in this class, what happens is it can contain any code we want, but any names we assign to in the class body get added as attributes to the class object. So in this class statement, a class object is being created, which inherits from Kate. That class object has two attributes, one x with the value 3, and the other named whale with a function object. And once created, that class object itself is assigned to the variable Jack. Notice that the function here, whale, its first parameter is called self. That's a convention of Python classes. Because the function in this class is going to be effectively a method, the instance object should normally get passed in as the first argument to the function, and the convention in Python is to refer to the instance and methods as self. If you create a class and don't specify a parent class, implicitly the new class will inherit from object. Actually, in these cases, you don't have to write the parentheses at all. We can simply omit them. In any case, now that we have our class object, we can create instance of this class by simply invoking it. But now, what about constructors, and what about giving our instances their own fields? A class in Python is effectively given a constructor by giving it a method with a special name, init with double underscores. When we create a new instance, Python will implicitly invoke this function as a method on the new instance. So now in this example, when we instantiate Jack, the new Jack object gets passed to self in the init function. And so when 4 is assigned to the attribute foo of self, that's giving the new instance an attribute foo with the value 4. That's how in Python we get constructors and fields. The init function acts as the constructor, and in that constructor you can give the instance fields by assigning it attributes. Now, for many classes, we want the constructor to effectively be parameterized. We want to supply input when we create instances. We can have this in a Python class if we simply give init more than one parameter, and then when we instantiate the class, we must provide arguments to pass to these parameters. So here, when the init function has parameters a and b in addition to the first one, self, and we instantiate Jack with the arguments 8 and 4, well, per usual, the new Jack instance is passed to self, but 8 here is passed to A, and 4 is passed to B. So when we add A and B, we get 12, and so 12 is assigned to the attribute foo of the new Jack object. Now, in the parentheses where we specify the parent class, we can actually specify more than one because Python supports multiple inheritance. It's possible for a single class to have more than one direct parent. Here the class Aaron has two parents, Natalie and Jack, and notice they're separated by commas. The question this raises is how does it affect attribute searches, because attribute searches are the essence of the inheritance relationship in Python. Well, the rule for this turns out to be slightly complicated, so I'll give you just the brief version, which is that the search is done breadth first rather than depth. So in this example, the attribute search goes from Aaron to Natalie, and then to Jack, and then to the parent of Natalie, Simon, and then to the parent of Jack, Kate, before finally going to object there at the top of the hierarchy. The alternative to this search behavior is if Python were to do depth first rather than breadth first. In a depth first search, Python would check Natalie and all of its ancestors before it would even look at Jack and its ancestors. Actually, depth first is how Python did this search in earlier versions. In Python 3, however, it's always breadth first. And lastly, do note that it matters the order in which we write the classes in the parentheses. So here, because Natalie is listed before Jack, the attribute search checks Natalie before it checks Jack. Fortunately, in practice, multiple inheritance just isn't used all that often. One reason being that it's simply just kind of confusing. The other reason being that generally it's not all that useful. However, Python, unlike some other languages, does allow for multiple inheritance. Each file of Python source code is called a module. For every module which is run, the Python interpreter creates an object to represent that module, and as that module executes line by line, any names that get assigned at the top level of the module, that is, any assignment which is not inside a def statement or class statement in that module, those assigned names get added as attributes to the module object. So, once a module finishes executing, we're left with this module object that contains attributes for everything that was assigned in that module. This is how you can have multiple modules tied together. Within one module, if we want to invoke, say, a function defined in another, we just need to access it as an attribute from the module object representing that other module. Consider this example. Say we have two files of Python source code, one called april.py, the other called june.py. In the April module, two names get assigned to at the top level. First, a variable x is given the value 3, and then the def statement creates a function object which it assigns to the variable foo. So the April module object ends up with two attributes, x and foo. Over in the June module, we can access the April module by importing it with an import statement, which we'll explain more in detail later. But in short, what happens with the import statement here is first Python looks for a module called April. If that module has not yet run, Python will execute that module and create an object module for it. And then back in June, the import statement is implicitly an assignment. In the module June, the name April is being assigned the April module object. So then in the next line, when we write april.x, that returns 3. And if we write april.foo, that returns the function foo defined in April. If, however, we write april.y, well, the April module has no y attribute, so this will throw an exception. When we start the Python interpreter, we need to specify one module for the interpreter to run, and that module runs, and in course of doing so, it may import other modules, thereby causing them to run. It may happen, though, that a single module needs to get imported by multiple other modules, and so in the course of running, a single module may end up imported more than once. When this happens, though, the interpreter will only actually execute the module the first time it is imported. For all subsequent imports, that import simply uses the existing module object. So at first it may seem that a module is sort of like a function. It's this piece of invocable code, but it's really not like a function because it's guaranteed by Python only to run once in the course of that program. And also, of course, unlike functions, modules don't have parameters and they don't return a value when they're done executing. I mentioned briefly before that local variables in a function of Python get created implicitly by assignments. Recall, though, how things work in JavaScript. In this JavaScript function, x here is a local variable because the function foo has a parameter named x, but the variable y here is not local because the function foo has no parameter named y. To make it a local variable, we have to explicitly declare that this function foo has a local variable y with a var statement. In the Python version of this function, again, x is clearly a local variable because there is a local parameter x, but y is also a local variable just by virtue of the fact that we assign to y in this function. That raises the question then, what if in the function you want to assign to a variable which is not part of the function? Well then, we have to do the inverse of what we do in JavaScript. In Python we have to explicitly declare that a variable is not local to the function. And one way to do that is with the global statement. Here the statement global y is declaring that in this function, y refers to a global variable. Global here meaning really a variable of the module. So now the assignment of 3 to y is assigning 3 to y of the module, not a local variable y. There is no local variable y in this function. Now, be clear that in cases where you just need to use a non-local variable, you don't need to declare that variable as non-local. You can just use it. And as long as you don't assign to a variable of that name in that function, Python understands that it's not local. So here in this function, if you write y assigned to x, well, x of course is local, but y isn't, as long as there's no y being assigned to in this function. Again, recall how JavaScript treats variables in nested functions. Here in the function bar, the interior function, when we assign it to y, the function bar doesn't have its own local variable y, so this must be something from the enclosing scope. In this case, it's y of the immediately enclosing function. If we want y in bar to be a local y, we have to declare it as such with a var statement. In Python, in contrast, when we don't explicitly declare that y is non-local, it's assumed to be local just by virtue of the fact that we are assigning to it. If you want y in the function bar to actually refer to y of function foo, you have to declare it as such with a non-local statement. The non-local statement tells Python that this variable belongs not to this immediate function, but to some enclosing function. If instead of declaring y as non-local, we declared it global, that would mean that y in the function bar refers to y of the module, not y of the enclosing function. So, to sum up the rules, if a name is assigned to in a function, it is then a local of that function unless it is declared to be global in that function or non-local in that function. The difference between the two being that global makes it a variable from the module, while non-local means it must be a variable from some enclosing function. Now, a subtle but important rule to keep in mind is that when you declare something non-local, there must actually be a variable of that name in an enclosing function. If there is no such variable, Python considers that an error and will throw an exception. Understand though, this is only the case with non-local. If you declare in a function a global variable which doesn't actually exist in the module, that's perfectly fine, because when in the function you actually do assign to that name, it will create the module variable of that name if it does not yet exist. That's a reasonable thing to do with modules because names assigned in modules are really just attributes added to the module object. It doesn't make any sense to do the same thing with non-local variables because how would you add a new local variable to some enclosing function? It just doesn't make any sense. So that's why Python has the double standard. When you declare a variable to be non-local, Python requires that such variable actually exist in an enclosing function. The body of a class in Python is considered its own scope, but classes aren't really like functions. The variables we declare in classes become attributes of the class object. They're not really local variables. And moreover, classes have no concept of closure, so it's really a quite different thing going on in classes than compared to functions, even though they are both scopes. And it is possible, of course, for a class to be nested inside a function, or to be nested inside another class, or to have other classes and functions nested within it. But the odd thing with classes is that any scope nested within a class cannot see the scope of the class itself. So here, for example, in this class Stephen, we are declaring a function foo, and that function definition of foo is itself its own subscope of the class Stephen. Inside that function, we can't directly refer to anything in the scope of the enclosing class. So here in the function when we return Mark, presumably meant to refer to Mark assigned in the Stephen class, this actually doesn't work because Mark of the Stephen class is not visible. So the way around this is in the function we can refer to Mark indirectly via the reference to the class object itself, because the class object is assigned to Stephen in some enclosing class, which the function can see. So Stephen.mark will work. That assumes, however, that Stephen itself is not created directly inside another class, which would be an odd thing to do, but it is legal. So here, when Stephen is being created inside Kelly, so Stephen becomes the only attribute of the Kelly class, inside that function foo to refer to Mark, we now have to write Kelly.Stephen.mark. Here we have to assume Kelly itself is not declared directly inside some other class. We have to assume it's, say, part of the module or created in some function. Because, again, the rule is that inside a scope, you cannot see the scope of any enclosing class. Because a class is a kind of scope where assignments to names implicitly become parts of that scope, this means we have to use the non-local and global statements if we want to assign to a name in that class body and have that name refer to something from an enclosing scope or the module scope, rather than refer to an attribute of the class. This in truth would really be an odd thing to do, but I mention it really just for completeness and to drive home really how the scope of a class body works. Python includes an important special module named built-ins, so called because it includes dozens of commonly used built-in functions and classes, such as, say, the print function, which prints text on the console, a function called abs, or for absolute, which returns the absolute value of a number, or, say, the classes like stir and object. These things are all placed in the built-ins module. If you were to import built-ins, that would assign to the name built-ins the built-ins module object, and then if we write built-ins.print, that would get us the function print from the built-ins module. And so here if we write built-ins.print with the argument 3, that would print the number 3 on the console. The special thing about the built-ins module, however, is that we can access its attributes directly. We don't have to import it. So rather than writing import built-ins and then built-ins.print 3, I can simply write print with the argument 3. The reason this works is because when you use a variable name, Python searches for that name first in the local scope of where we are, say if we're in a function, And then if it's not found there, it'll look in the enclosing scope, say any enclosing other functions. And then if it's not found in any of those, it then looks in the global scope, aka the module scope, the module. And if it's not found there, it'll then search in the built-in scope. So in Python, we call this the rule of LEGB, local enclosing global built-ins. When Python needs to resolve a name, first it looks in the local scope, then the enclosing scope, then the global scope, aka the module, and then the built-ins module. The local enclosing global part you're already familiar with. That's basically how JavaScript works too, but the thing Python adds is that it then goes and looks in this fourth place, the built-ins module. So again, generally when we want to access an attribute of the built-ins module, we don't access it per usual as an attribute, we just refer to it directly by name. Now, the way this works does mean it is possible to effectively obscure names from the built-ins module. For example, if in the current module we were to assign to the name print some value, say here the value 9, now if we try and invoke print as a function, well, print isn't going to be found in the built-ins module, it's going to be found here in this module itself, and we're going to get an error here because you can't invoke a number as a function. Generally, Python programmers solve this problem by simply avoiding assigning to names found in the built-ins module. An interesting thing to note here is that this is the only case where it's possible for the use of a variable name to actually change which scope it resolves to. Imagine, for example, that in some function we invoke print. As long as that function itself and none of its enclosing functions and its enclosing module have no variable themselves called print, that print in the function will resolve to print of the built-ins module. But because modules are mutable, that is, attributes can be added and removed, it's possible for that print in the function to change what scope it resolves to. If we add print to its enclosing module, then that print in the function will no longer resolve to print of the built-ins module, it will resolve to print in its enclosing module. And in fact, the reverse can happen as well. If a name resolves to something from the enclosing module, if we delete that attribute from the enclosing module, then it might resolve to something of the same name in the built-ins module. So in short, it's possible for a name that resolves to something in the enclosing module to switch to resolve to the same name in the built-ins module, and vice versa. The switch can go the other way. This does not happen with the local variables of functions. The local variables of functions are effectively fixed in which scope they resolve to. Very briefly, we can see this happening in action. Here's a function foo, which invokes print from the built-ins module, and if we invoke foo the first time, that's okay, it prints hello, but then if in that module we assign to print some number, something which is not a function, and then we try and invoke foo, well then print inside the foo function is going to resolve to print of the local module now, and that's a number, not something we can invoke, so this is going to trigger an error, it's an exception. So finally now, if we wanted to create the Hello World program in Python, it would simply be a module, a single source file, consisting of just this line, print with the argument Hello World as a string. When we run the Python interpreter and we don't specify any module to load and run, Python then runs in interactive mode. In interactive mode, Python gives you a prompt at which you can type a statement of code, and then you hit enter and Python will run that code. Effectively, interactive mode is like as if we are writing a module of Python code line by line, and every time we hit enter, it runs that code immediately. The utility of this isn't really all that great. I do, though, like to use Python as my calculator, and this interactive mode does come in handy for people learning the language because it's nice. You can just start up the interactive mode and try a few things and see what happens. Notice here in this interactive mode, when I wrote a line that triggered an exception, normally an exception that isn't caught in Python will basically abort your program, but here in the interactive mode it simply just prints out the exception message and then lets you continue on to type more statements. The last thing we'll talk about in any detail here is how Python treats exceptions, which are basically the same as we saw in JavaScript, except a few terms have changed. First of all, what JavaScript calls a catch clause in Python is called an accept clause, and where JavaScript has a throw statement, the Python equivalent is called raise. In Python we usually say an exception is raised rather than thrown. The big difference in Python is that a try may have multiple accept clauses, and when an exception is thrown in the try, the except clause which executes is the first one which lists a class of which the exception object itself is an instance. So here in the example we have a try with 3 except clauses. The first except clause lists a class Amy, the second has 2 classes, Carol and David, and the third except clause doesn't list any classes, which means that it will match any exception. So if in the try block here an exception is thrown, Python tests whether or not that exception is considered an instance of the Amy class. So it must either be an instance of the Amy class directly, or it must be some instance of a descendant of Amy. And if that test proves true, if the exception is an instance of the Amy class, then that first except clause is the one that runs. Failing that, however, Python then goes on to test the subsequent except clauses. And so here it will test if the exception is an instance of either the Carol class or the David class or both. And if it matches either one of those or both, then that except clause runs. But then failing that, if we get to this last except clause that doesn't have any class specified, well, this except clause will match any exception object. So this effectively serves as the default exception clause. To restate all that, when an exception is thrown in a try, Python looks for a matching except clause in order, top to bottom, testing by type. And when a match is found, that is the except clause which runs. In a case where no except clause matches, then the exception will propagate. And finally, the last thing to say about exceptions here is that whereas in JavaScript an exception can be an object of any type, in Python exception objects must be instances of the base exception class. That is, they must directly be instances of that class, or they must be instances of some descendant of the base exception class. That aside, the big new idea with exceptions in Python is that an exception thrown in a try is matched to an except clause by type. That's the one big conceptual change. We have a few more things to say about exceptions, which we'll cover in the supplementary material. Now, in the supplementary material we actually have a lot to talk about. There's a good 100 pages or so of material in there, really. And that's all because Python is actually quite a complicated language, especially compared to Pidgin and even compared to JavaScript, which is a real-world language. So very, very briefly, here's most everything we'll cover in that supplement. First off, truth value. Just like in JavaScript, where every object effectively has a truth value, not just the Boolean values of true and false, well, the same is true in Python. We'll talk about those rules. The logical, relational, and equality operators, those are the operators like and, or, greater than, less than, equals to, not equals. We have to discuss those in a bit more detail. Functions in Python can be declared to have special kind of parameters, and then when we invoke a function, we can supply the arguments in special ways. And these special mechanisms are, say, how we can invoke a function with some variable number of arguments, just like we can in JavaScript. A sequence in Python is a list or list-like data type, and a mapping in Python is a dictionary or dictionary-like data type. And in the supplement we'll go over the many different operations which you can perform upon sequences and mappings. Then we'll talk about tuples, sets, ranges, iterators, and view objects. These are all different kinds of collection objects. A tuple, for example, is really just a list which is fixed, meaning you can't add, remove, or modify any of its items. The rest we'll explain in due course. We haven't discussed all the different ways you can write number literals or string literals in Python. There are a few different ways. And then there are rules in Python for allowing us to deviate from the rules of strict indentation. Like, say, you might have a very long function call where the arguments you want to spread them onto multiple lines. There's a rule that allows you to do that. We need to talk about number types because there's actually more than one number type. It's not like in JavaScript where you just have one type of number. There's actually a separate type for integers and floating point values. And then Python has a few additional handy constructs for doing control flow, such as the for loop, and a few other things can have else clauses on them. And a del statement, del short for delete, is a statement beginning with the reserved word del, which we can use to remove things from lists and dictionaries, and also remove attributes from objects, and say remove variables from the current module. A lambda expression in Python is, oddly enough, the equivalent in Python of writing a function as an expression. Because recall, in JavaScript we can write a function as either a statement, just like we do with the def statement in Python, or we can actually write it as an expression that returns a new function object. Lambda is Python's equivalent. It's unfortunately not as flexible and therefore nearly as useful as function expressions in JavaScript, and that mainly stems from the limitations of Python indentation syntax. This is actually the one thing I find regrettable about the indentation syntax. Also in the supplement, we need to go over the few dozen or so classes and functions found in the built-ins module, and then we'll explain exactly how the import statement works, and then we have what are called packages, which are basically bundles of modules, and then there's variations of import with the reserved words from, and also there are what are called relative imports. And then there's this very neat way of creating lists and sets and dictionaries called comprehensions. We'll explain those. Generators, as we'll explain, are effectively special kinds of functions which suspend themselves in the middle of execution and then later get resumed. Generator expressions are just a special way of creating generators. Destructuring is just a fancy term referring to this feature that allows us to conveniently assign items from collections, from dictionaries and lists, to variables. That's all it is, really. And then Python has what's called a with statement, which is mainly used in conjunction with files. In short, the most common use of with is it makes sure that when we open a file that we actually close it when we're done with it. And then the bytes type, that's effectively a data type which represents some sequence of bytes. And a byte array is just a variant which is mutable. The bytes type is immutable, just like strings are immutable. And then we will discuss all of the various methods found in the string class. There are many different useful methods there. And then finally, at the very end, we'll discuss meta-classes, which are really a very kind of obscure feature of Python. They're really very weird. Basically, imagine a class for defining the creation of classes. They are really not used very often because they are really kind of weird, but we will cover them for completeness sake. And so that's everything pretty much we'll cover in the supplement. It's not light reading, but it's as short as I could make it. And all of that, though, including what we've already covered in this lecture, that's all just the language Python proper, the rules of its syntax and semantics. In practice, though, when you write actual Python code, you're going to need a lot of stuff found in Python standard libraries. Python standard libraries are really quite extensive. First off, you have these three modules, one called Math, one called Sys, and one called OS. Those are a good place to start. Math obviously has stuff for doing some basic math, like, say, trigonometry. The Sys module, Sys short for system, includes things having to do with getting information about the system environment, and OS, somewhat related, has to do with the operating system environment. And then beyond those three, you'll want to learn how to use regular expressions in Python. Regular expressions, if you don't recall, are a tool for doing complex search and replace operations in strings. And very importantly, you'll want to figure out how to do input and output on the console, how to work with files. What Python calls pickles, shelves, and marshalling, that all has to do with storing Python objects in a persistent state, that is in some database or in a file, and then retrieving them, loading them in your program. You'll want to learn about how to deal with sockets for networking, how to do web stuff, like make an HTTP request, maybe deal with FTP and email. You'll want to learn how to use some library to interact with a database. And there are libraries for doing graphical user interfaces, GUIs. One popular one is called WXWidgets. There's another one called Qt, and a really ugly old one called Tkinter. And then, if you really want to get advanced, Python, or at least CPython, has a feature that allows you to create a Python module partly in C code. This is something you would do generally for efficiency reasons because Python is not particularly good at, say, number crunching. C does that much more efficiently. So that might be something you wish to learn, how to write a C extension for Python. Though, of course, it's something you'd probably learn after learning C itself, which we'll do later. While Python does have a Boolean type, it has the values true and false. For the sake of condition expressions, like say the condition of an if or a while, those expressions don't necessarily have to evaluate into Boolean value. They can actually evaluate into any kind of value. And this is the case because for the purpose of a condition, Python considers all objects to have a truth value. And obviously the Boolean value false has the truth value of false, and the Boolean value true has a truth value of true, but what about other objects? Well, first off, the special value none is a special case that's always considered false, But all other objects, such as say the instances of a class you create, those are by default considered true. If, however, an object has a special method bool, bool, or a special method len, short for length, then one of those two methods is used to determine the truth value of that object. The bool method of an object should return either true or false, and that returned value represents the truth value of the object. If, however, an object has no bool method and it only has a len method, then the len method is invoked, and if it returns 0, that's signifying that the object has a truth value of false. Any other returned value signifies a truth value of true. So, for example, the standard number types of Python have a bool method but no len method, and so their truth value is determined by invoking this bool method, and the way that bool method is defined for the number types, it will only return false if the number is equal to 0. Effectively then, all number objects in Python have a truth value of true, except those which are equal to 0. As for the len method, well, the standard collection types, the list type, the dictionary type, and their related types, they all define a len method but no bool method. So when Python wants to determine the truth value of, say, a list, it invokes its len method, and if len returns 0, then the list is considered false. And of course the len method is short for length, so it's returning the number of items in that collection. So effectively, list, dictionary, and string objects in Python are all considered true except those which are empty. So if you have an empty list, an empty dictionary, or an empty string, their truth value is false. So to sum it up again, all objects in Python have a truth value of true except for the Boolean value false, the special value none, numbers equal to 0, empty strings, and empty collections, and for the sake of any classes you yourself define, the truth value is determined by the bool or len method, and if you give your object both the bool and len method, the bool method is used to determine the truth value instead of len. Whereas in JavaScript and Java and C, and in fact most popular languages, the and or operations are represented by double ampersands and double pipe symbols, in Python they're represented by the reserved words and or. And likewise, instead of an exclamation mark for the not operator, not is just written as the reserved word not. Now, when it comes to the actual operation of these operators, the not operator acts like you expect. It returns the inverse truth value of whatever the operand is. So here if x is true, then not x will return false. And if x is false, then, or has a truth value of false, then not x will return the Boolean value true. But as for the and or operators, they actually have a short-circuiting behavior just like they do in JavaScript. So surprisingly, in some cases, only the left operand is evaluated. The right operand might go unevaluated. So if the right operand is, say, a function call, well, that function call may not get invoked. Also surprising is that the and or operators don't necessarily return a Boolean value. They don't necessarily return true or false. Instead, they return one of the two operand values. So in the expression x and y, Python will first evaluate just the left operand, here the expression x. And if the value of that expression has a truth value of false, then that object is what is returned by the expression x and y doesn't get evaluated at all. However, if the value returned by the left operand expression, here x, has a truth value of true, then the right operand expression, here y, will get evaluated, and the value of that expression, the right-hand operand, is what's returned by the and operation. So to put it succinctly, if x is false, then we return x, but if x is true, then we return y instead. Now, if you think about it for a moment, this makes sense, because if in an and operation you test just one of the operands and discover that it has a truth value of false, well then, you don't need to evaluate the other operand. You already know that the and operation is supposed to return a false value. And moreover, instead of necessarily returning the Boolean value false, we can return the value of that first expression itself, because we already determined that, hey, it has a truth value of false. So whatever object that is a suitable substitute for the Boolean value false. Now, in the case where the left-hand operand evaluates true, well, at that point we then know that the value of the whole operation, the and operation, is equivalent to the value of just the right-hand operand by itself. If x is true and then it turns out y is also true, then we know that the AND operation should return true. But if x is true and then y is false, then the AND operation should return false. So the correct truth value of the whole AND operation is synonymous with the value of just the right-hand operand by itself. So, in the expression x and y, we evaluate x, and if it turns out to be true, then we evaluate y and return that object as the result of the AND operation. As for an OR operation, everything works out the same, except we just invert the truth test. So when we evaluate that left-hand operand and discover that it's true, then we return the left-hand operand itself. Otherwise, if it's false, then we evaluate the right-hand operand and return that as the value of the expression. Because if you think about it for a moment, if we're testing whether x or y is true, once we've tested x and discovered that it is true, we don't need to know what y is. It can be true or false, and the value of this OR operation is still going to be true no matter what. However, if x turns out to be false, well, it's still possible for y to be true or false, and that still matters, because if it's true, then the OR operation should return true, otherwise it should return false. For a quick example here, we have an OR operation with a left-hand operand of just 3, and a right-hand operation that invokes foo. What happens here is that first the left operand expression is evaluated, and its truth value determined, and 3 has a truth value of true, because all non-zero numbers have a truth value of true in Python. And so at this point, having only evaluated just one of the operands, we already know that the OR should return true, so we don't need to evaluate the other one. We don't have to actually call the function foo here. So this OR operation will return the value 3 without actually evaluating here the call to foo. It's always important to distinguish in any language between an equality test and an identity test. An equality test is asking whether these two objects have the same content effectively. So two number objects can have the same value. You can have an integer value 3 and a floating point value 3.0 and consider them to be equivalent even though they aren't the very same value. An identity test, in contrast, is not asking whether two objects have the same content or whether they represent the same value. It's asking whether these two objects are actually one and the same object. So, with the important difference in mind, to perform an equality test in Python, the operator is a double equals sign, like what you find in most languages, and then the logical inverse, the not equals operator, is written with an exclamation mark equals sign. And like most operators in Python, these two operators are really method calls in disguise. The equality operator invokes the EQ method, whereas the inequality operator, the not equals operator, invokes a method called NE, as in not equals. As for identity tests, the operator is written as the reserved word is, and then the logical inverse of the is operator is written as is not. And be clear that though is not is written as two separate reserved words, it's really one single operator. You shouldn't think of it certainly as the is operator followed by a not operator. That's not what's going on here. It's just one operator that happens to have a space in the middle. Actually, if here in this example we were to put parentheses around the not y portion, then that would be a use of the not operator producing some Boolean value, either true or false, and then we'd have another is operation, x is either true or false. And in that case, yes, it would be two separate operators, but here without any parentheses separating is and not, they're together treated as one operator. Now, if you're wondering why the identity operators here, is and is not, do not have corresponding methods like the equality operator does or the not equality operator does, well, the answer to this is that object identity is not a type-dependent concept. What it means for any two objects to be identical doesn't change depending upon the types of the objects. It's not like some class you define is going to have its own special notion of what identity means. That's not the case. Whereas with equality, that may very well be the case. For example, in the case of numbers, there are cases where two numbers can be equivalent without them being exactly the same. For example, the integer value 3 and the floating point value 3.0, those two values we consider equivalent even though they're not precisely the same. And so what you may find when you create your own data types, your own classes, you may want to have some special definition of what equality really means for that type. So for your own class, you may want to define what the equality and inequality operators mean, whereas you wouldn't want to do that with the identity operator. There's no reason you would ever want identity to mean something other than just these two objects are precisely the very same objects in memory. Now, somewhat confusingly, if you define a class and you don't give it its own EQ and NE methods, well then that class will simply inherit the methods from object. And the way these two methods are defined in the object class, they return true when the objects are identical. So effectively, by default, the equality operator used on class instances does the same thing as an identity test. Now, when it comes to the relational equality and identity operators, Python has a special rule when you have them one after the other, when you have them in a chain. Looking at this example JavaScript code, when you see x less than y less than z, that's almost certainly a mistake, because when you write x less than y less than z, what you expect that to do is to return true if x is less than y and y is less than z, but that's not how JavaScript interprets it. In JavaScript, this would be executed as first x less than y returning a Boolean value, and then the other less than operation, the whatever less than z, doesn't make any sense anymore because you can't use a Boolean value in a less than comparison. So the proper way to express this in JavaScript is to write x less than y and y less than z. It's really two separate comparisons, and we logically AND them together. In Python, however, you can actually get away with expressing the same logic either way. You can do it as you would expect to write it in JavaScript, or in fact most other programming languages. You could write x less than y and y less than z, or you could just write x less than y less than z, because Python has a special rule for chained relational operators appearing one after the other, not separated by parentheses. And what this special chaining rule does is it takes an expression of this kind and splits it up into separate relational operations connected by the AND operator. So Python takes x less than y less than z and magically converts it into x less than y and y less than z. And this special chaining behavior works not just with relational operators like less than or greater than or less than or equal to, it works also with the equality operator, the double equal sign or the not equality operator. And it also applies to the identity operator, so is or is not. And be clear that this rule applies when you have a mix of these different kinds of operators. So you can write A not equals B greater than or equal to C is D, and Python will magically insert as many AND operators as is necessary. Now, the only thing to watch out for here is that occasionally, it's conceivable at least, you can have a scenario where you don't want this magic to be applied. And the way you suppress it from being applied, the special chaining rule, is just use parentheses to make your intention explicit, and then Python won't insert any AND operators. To be honest, I actually wish Python didn't have this special chaining syntax, because it's really unexpected coming from most other programming languages. I tend to avoid it and just make all my AND operations explicit, and I believe most Python programmers do the same. Python has another syntactical allowance, which is usually called chained assignment, but don't let the name confuse you, because it doesn't really have anything to do with the chained relational equality and identity operators. This is just really the allowance in Python that lets you write x equals y equals z equals 4. Remember that unlike in most languages, Python doesn't allow assignment as an operation. When you write an equal sign in Python for assignment, that's a special kind of statement, not an operation. So in Python you can't write something like what you see here in the second line, where we have this y equals 2 used as an expression, as an operation that returns a value, because in Python that's just not the case. An assignment is a particular kind of statement. However, it is a nice convenience to be able to assign a single value to multiple variables in one statement, and so for that, Python has the special chained assignment syntax. Just be clear that in Python, assignment is a statement, not a kind of operation. Unlike in JavaScript, where all numbers are stored internally as floating point values, as the same data type, in Python, integer values and floating point values are separated by two separate data types. The integer type is called int, and the floating point type is called float. So if you see a number literal reading 3.6, that's a float value, 3.6, and if you see a number literal like 6 with no decimal point, that's an int value. Now, the class objects representing these two data types are found in the built-in namespace, predictably assigned to the references int and float. If you have a float value and you want the corresponding integer value, you can pass that float to the int constructor,
and that'll return an int value, which is the rounding of that float. So int 3.6 will return 4, and conversely, if you want a float value from an int value, then you pass the int to the float constructor, and that'll return the float equivalent. So float 6 returns a floating point value of 6.0. Now, an important thing to keep in mind is how these two data types are represented. Float values are represented in the IEEE 64-bit floating point format, just like in JavaScript. This means that when it comes to floats, you're dealing with limited precision and magnitude. Float values can only get so accurate and so large. For most purposes, these limitations aren't really relevant. You're not going to bump into them, but depending upon what you're doing, if you're doing highly precise math calculations, it's something you may need to keep in mind. Python's int type, on the other hand, has no size constraint, meaning Python will use however many bits are necessary to represent an integer, even if that means creating integers that take up megabytes of memory, which would be very extreme and not something that would occur commonly, but Python is capable. So for all intents and purposes in Python, you can represent whatever integer value you want, and the only limitation is that you can't deal with integers so large that they exceed the entire storage capacity of your system, which frankly would be a very absurd thing to happen. Now, in addition to ints and floats, there's actually a third number type for complex numbers called complex, and the way to express a complex number as a number literal is to write the imaginary portion suffixed with a j. Why the letter j and not I? I believe that's simply because it was decided that the letter I in a lot of programming fonts doesn't stand out well enough. It looks too much like an L or a 1, so instead they went with j. In any case, if you then want to write a complex number with a real portion, then you just add a regular integer to the imaginary number, and that will return a complex number. Alternatively, if you write complex, which is found in the built-in namespace, you just write complex and then pass the real portion as the first argument and the imaginary portion as the second argument, then that returns also a complex number. Python also has a syntax for expressing int values in hex, octal, and binary, and these are written simply by prefacing the number with 0 followed by the letter X for hex, O for octal, or B for binary, and those letters can be uppercase or lowercase, though I think lowercase is generally more readable. And then also if you want to express float values in engineering notation, aka scientific notation, then you just write the mantissa portion, the significand, followed by E, and then the exponent. While the normal division operator is expressed as just a single slash, there's also a double slash operator which does what Python calls floor division. And floor division simply rounds the answer down to the next integer. So 8/3 returns the int value 2, not 2.66666 as you would normally expect with regular division. And then same deal with 8.0/3, it returns 2, except this is a floating point value because the operands here included a float. And generally anytime you mix a float and int operand together in an operation, it'll return a float. And then finally the last example, -8/3. Notice that it rounds down from -2.666 to -3. So it's not rounding towards 0, it's always rounding down to more negative. Now, one of the biggest gotchas in Python is actually something which Python 3 fixed, but the gotcha in Python 2 and earlier was that the regular division operator, when both operands were ints, it would return an int value, even if the correct answer, the mathematical answer, you would expect to be a float value. So, for example, 8/3 in Python 2 would return the int value 2. And the trick you had to use to get the answer which you normally wanted was to make sure one of the operands was a float rather than an int. So, for example, if you write 8/3.0, well, 3.0, that's a float, so the answer we get back is going to be a float, and it's going to be correct. It's going to be the float value 2.66666. When you have a long, complex line of code, especially say when you have a function call with many arguments, or say a list literal or dictionary literal with many items, it's often desirable in such cases to take that one big line and spread it onto multiple successive lines to make it more presentable. While Python syntax is not free-form, it does have a special rule to allow for this, and that is the rule of open delimiters. If in your line of Python code you leave a delimiter open, whether an open parenthesis or an open curly brace or an open square bracket, then until the matching closing delimiter is encountered, Python's usual rules about indentation and one statement per line, those are temporarily deferred. So here, for example, if we have this line x equals and then this long complicated call to foo with many arguments, well, we can take whatever in the parentheses there and spread it onto the succeeding lines however we wish. Only when Python encounters the matching closing delimiter, the end parenthesis here, do the normal indentation rules resume. So here, after the end parenthesis, we can finish off the line with *98, but on the next line, the usual rules resume. So the call to bar has to be aligned how you see it here. It has to be aligned with the statement which precedes it, which starts with x equals. Now, when I have a function call with many arguments, or a list literal with many items, or a dictionary with many items, I like to format it like so, where all the successive lines are indented one level underneath of the line where it starts. And then I place the closing delimiter level with the start of the original line. And I do it this way because it mirrors how I format my curly braces in curly brace languages like JavaScript. Of course, you don't have to imitate this precisely, but I do strongly recommend that you settle upon some formatting style and stick with it. Again, be clear that this special rule applies not just to parentheses, but to all delimiters. So here, for example, is a square brace being left open, and then that logical line doesn't end until you encounter the line with the matching closing square bracket. As another stylistic affordance to get around the usual rules of indentation, Python also lets you use a backslash at the end of the line to indicate that that line actually continues on to the next line. So think of it simply as a marker that says this line is not over yet, it actually continues on to the next line. So here, for example, we have one logical line, but it's actually been written across 3 separate lines, and it reads just simply x equals foo plus bar times 3 times 98. Now, there is one important gotcha, and that's if a line ends with a backslash, that line cannot also have a comment. If you put a comment on the same line, that's a syntax error. In my opinion, you should really never use the backslash. It's just more trouble than it's worth. The open delimiter rule should really serve all of your needs. For yet another stylistic allowance, if you have a code block consisting of just one statement, you can write that statement on the same line as the block header. So here, for example, you see an if and a function definition, both of which have just one statement in their bodies, so they're just all written on one line. It's also allowed, using semicolons, to write multiple statements on one line. The only limitation that these statements must be just either expression statements or assignment statements. They can't be statements like an if statement or a function definition statement. So here we have on one line 3 statements, x equals 7, an invocation of foo, and then an invocation of bar. And those, of course, are executed left to right. So it's really just the same as writing them on 3 successive lines. It's just a stylistic choice here to put them on one line. And in fact, you could use a semicolon to put multiple statements in a one-line block. So here this if block has 2 statements, first a call to foo and then a call to bar. Like the backslash for line continuation, I never use multi-statement lines or one-line blocks. I think they're just bad style. Yeah, they do let you write your code a bit more compactly, but it's really not worth it. You're just making your code harder to read at a glance. A pass statement is a statement consisting of just the reserved word pass, and as the name implies, a pass statement does nothing. It passes over execution. So it's just a placeholder statement, effectively. And the pass statement exists mainly because when you're writing out your code, you're writing your functions and your classes, when you just start out, typically you leave just a stub of a function or a stub of a class. You know, you write class and then the name of the class, colon, and then you don't actually put a body there because you haven't written it yet. And yet you want your code to actually still compile because you have other stuff you want to test or whatever. So you can't leave that body, that class header, without anything there because that would be a syntax error. So when stubbing out our functions and classes, we just write them with pass statements, and then we can run that Python module without getting a syntax error, even if the code is incomplete. Many of Python's operators, including the basic arithmetic operators, come in a compound assignment form. Basically, it's the combination of the operator with an assignment. So if you see x plus equals y, that means add x and y together, and then store the result of that addition in x. The purpose of this is simply that that's something we want to do commonly enough. It's nice to have a more compact syntax. In fact, this is the preferred syntax in Python for incrementing or decrementing a variable. So if you have a variable x and you want to increment it, you write x plus equals 1. And if you want to decrement it, you write x minus equals 1. And Guido considered this sufficiently convenient that he decided Python doesn't need an increment or decrement operator like you have in JavaScript and C and all those languages. So there's no minus minus operator or plus plus operator. The basic operator methods all have a corresponding reflected operator methods, which all have the same name except there's R in front. So say the add method has a corresponding reflected add method, which is called radd. Python invokes these reflected operator methods in a scenario where first the two operands are of different types, and if the regular method, the non-reflected method, is first invoked and then raises the not implemented exception. So here, for example, if we have the code 3 plus w, assuming w is the instance of some class we've defined, well, first Python will invoke the add method of the int object, and w will get passed as the argument, but the add method in this case will raise the not implemented exception because the standard int method isn't defined to add together a standard int object, the number 3 here, with some instance of a class you've defined. So it will raise the not implemented exception, and that triggers Python to then invoke the radd method, the reflected add method of the w object with 3 passed as argument. So assuming in this class you have defined an radd method, you can then have a defined behavior for what happens when the plus operator is used with instances of this class as the right operand. Now, assuming you want there to be a defined behavior with the plus operator and instances of this type, then you would give that type both an add method and an radd method, a reflected add method. And generally, in most cases, you will want them to basically do exactly the same thing. The only difference is that the radd method is invoked when the instance of the class is only the right operand. Normally, we assume that a plus operation is commutative. That's how addition is defined, right? It doesn't matter if you write a plus b or b plus a. However, with some types you might define, you might decide that you want there to be some non-commutative behavior. So you might want 3 plus w to do something different than w plus 3. So that's why we have this reflected add method, because sometimes you want there to be different behavior. If instead Python just assumed that these operations should always be commutative, then we wouldn't have the reflected operator methods. Python would just, after not implemented is raised, it would just invoke the regular add method of the right operand. But Python decided otherwise. It decided that sometimes we'll want to have non-commutative operations, so that's why it has reflected operator methods. Recall that in JavaScript, we can define a function by writing not just a function statement, but also by writing a function expression. And we can actually do the same in Python. It's just that whereas we define functions as a statement with the def statement, for a function as an expression we use a different reserved word, lambda. Why lambda? Well, lambda is a symbol used in lambda calculus that denotes a function. So that's the thinking behind the name. The unfortunate thing about Python's lambda is that it's much more restricted than a full-on def statement. When you write a lambda function, the body of the function can only consist of a single expression statement. You can't have any other kind of statement, and there can only be one. The real reason for the syntax is that if you want to include multiple statements or to have other kinds of statements like ifs and so forth in the body of the lambda function, that would require using indentation to denote them, and that just doesn't make any sense in the context of an expression. So if there's one real downside to Python's indentation-sensitive syntax, I would say this is it. This is the one thing I miss when I program in Python rather than JavaScript, the ability to write any function as an expression. Of course, the workaround to this is simple. Anytime you want to have a function that needs more than just a single expression statement in the body, you just write that as a regular function definition and then pass it by name where you need it. But what I think is surprisingly bothersome about having to do that is it means you have to give the function a name. And I'm always a believer in wherever you can get away without having to give things names, because the more names you have in your code, the more likely you're going to give them bad names that aren't very meaningful and that actually make the code harder to read and harder to understand. In any case, looking at this example, here first we have a regular function definition that's defining a function foo with the parameters x and y, and it just adds those two parameters together and returns that result. And then you have the same thing, just expressed with lambda. The function object returned by the lambda expression here is really exactly the same as the function object that gets assigned in the def statement to the variable foo. Notice that the parameters in lambda are listed before the colon and they're not included in parentheses. To define a function with no parameters with lambda, you just put the colon immediately after the reserved word lambda. So here again, same idea, we're defining a function with a def statement that takes no parameters and just prints hi, and then we're expressing precisely the same thing, just expressed using lambda. An important thing to know is how Python actually discovers, how it actually finds the module specified in an import statement. Well, the answer is that Python keeps an internal list of directories, and when you import a module, Python searches for a module of that name in these directories in order from first to last. So the order in which the directories appear in the list can actually matter. You can access this list by importing the sys module. Sys is short for system, and as the name implies, the sys module is a standard Python module that contains things related to the system itself, the environment in which Python is operating, and this module's attribute path references the list of directories which Python uses when it searches for a module. Now, you can actually modify this list, and if you do, that will affect any future imports. So here we import the sys module, and we're appending a directory path /home/Brian to the end of sys.path. So now in subsequent imports, Python will look in that directory to find modules, though this is being appended to the end of the list, so it's the directory which will be searched last. Which again can matter, because if we're searching for a module, say, named foo, and if there's a foo module in more than one of the directories in sys.path, well, whichever one is found in first, that's the one Python will use. Now, as for what directories you'll find listed in sys.path by default, that depends on the platform. It'll differ in Windows from in Linux. But the gist is that on any platform, by default, you'll find in sys.path directories which contain modules from the standard Python library. So you should be able to import standard library modules without having to modify sys.path. Also understand that the directories listed in sys.path can be expressed either as absolute paths or as relative paths, and the relative paths are interpreted as relative from the current working directory of the Python interpreter process. And in fact, if you start up Python in interactive mode, if you start up the Python shell, you'll find that the first path listed is just an empty string, which is effectively a relative path to the current working directory itself. So in effect, when you run Python in interactive mode, the current working directory is always going to be the first directory searched by imports. If, however, you run Python not in interactive mode, but by specifying the name of some Python module to run as your main module, then the directory of that module will be the first directory listed in sys.path. And that makes sense because normally the other modules of a program are placed in the same directory as the main module, or they're placed in subdirectories of that directory. Now, Python module files actually come in two forms. There's the .py files, which are source code files, the ones that you write, but when Python takes a source module, a .py file, it creates from that a compiled Python module called a .pyc file, or a pyc file. And the idea of these pyc files, these compiled Python modules, is that they're faster to load. That's the main purpose. The term compile here is a bit of a misnomer, because it's not like these files contain native code, and they don't really contain something like Java bytecode either. Really what it is it's simply just say, when you execute a Python module, the whole parsing of that source code and the creation of the functions representing the objects and the classes, well, that business can all take up a surprising amount of time at program start. So pyc files are basically pre-parsed modules with serialized function and class objects, which can just be read from the file into memory without having to actually produce those objects. And that can save quite a bit of time in processing on program startup. Now, you don't actually have to worry about creating these pyc files yourself, because the default behavior in Python is to just automatically create them for you. The way this works is that when Python searches for a module, there are basically three cases. There's the case where only foo.py exists, the regular source file. Then there's the case where Python only finds a file named foo.pyc and no corresponding foo.py file, and this situation might occur because someone could create a Python program and only distribute the pyc files rather than the source code. And then there's a third scenario where both files exist, where Python finds both foo.py and foo.pyc. Well, in the first case, when only foo.py exists, the source file exists, then Python will actually create the pyc file from foo.py, and then of course execute the module. In the second case, where only the compiled form is found, the pyc file is found, Python will simply of course just load the module from the pyc file. But then in the case where both files exist, then Python checks whether the py file is newer than the PYC file. That is, if the source is newer than the existing compiled module. And if that's the case, well then obviously what's happened is the programmer has updated their source code, and of course they want to have the compiled file updated to match. So Python will recompile the module. It will update the PYC file before then actually loading it. So the way this generally works out is that if you have a Python program all in source form, and then you run the program, then that first time the program runs, Python will produce all the corresponding PYC files, such that any subsequent time you run the program, it'll be loaded directly from the PYC files, instead of having to reparse all the source code and compile it again. The only exception being, if you modify any of the source files, then Python will notice that whichever source code files you updated now have a newer date modified date than the PYC files. So it will then update those PYC files. Which is convenient, because effectively what this means is that when you're working on a Python program, you really don't have to worry about manually doing any of this compile business. It all just is handled for you, and if you modify the source code, you don't have to worry about it accidentally using the outdated compiled form. It'll just recompile the code as necessary. What Python calls a package is basically just a directory of module files, all of which presumably relate to each other somehow. It's just a mechanism of grouping your modules into logical groups. In an import statement, we refer to the modules of a package using the dot operator, even though this really has not much at all to do with attribute lookup or anything like that. So here we have import foo.bar. This means to import the module bar found in the package foo. So Python will search sys.path for a subdirectory foo with a module bar in it. Now, the complication of packages is it's not just a directory containing the modules of that package, it also contains another file given the special name _init_.py. And the special init module of the package is really just a module like any other. It just has a special name, and you can put actually any code you want in init.py, really just like any other module, though you could just leave them blank, as I usually do. But then the special thing about the init module is that when you import the modules of that package, they get assigned as attributes into this init module. So here, for example, when we import foo.bar, what actually happens in the local namespace where we're importing foo.bar is that the name foo is assigned and nothing else. And here after the import, the name foo refers to the module object representing the package itself, the init.py file in that directory. And because we've imported the module bar of that package, foo.bar will resolve to that module. However, bar itself is not found directly in the local namespace. Also, any other modules of the package foo won't yet be found in the module object representing foo until such time as those modules themselves are explicitly imported. In fact, it's quite possible to import just the package itself without importing any of the modules contained therein. So here we import just the package foo itself, and until we explicitly import the modules of the package itself, like foo.bar, those modules won't be found in the package object, which is really just a module object. It's a bit confusing because the objects which represent the packages are really just regular module objects, just like those representing normal modules. Now, of course, we can have directories within directories, so we can have packages within packages. So here, for example, import eagle.whale.tiger.frog. This imports a module frog from a package called tiger, from inside a package called whale, inside a package called eagle. Though actually, as we just saw, you can actually directly import packages themselves, so we can't say for certain, just looking at this line of code, that frog is actually a module and not a package. Just remember that when you create a package directory, it always must contain an init.py file, even if you just leave it blank and there are no modules in the package. Now, because some module and package names are obnoxiously long, it makes sense that after import you'd want to assign these modules to some more convenient name. Like here, for example, if we import a module called supercalifragilisticexpialidocious, we can just assign it to an abbreviated name and use that instead to refer to the module. This is done commonly enough that Python has an optional clause in an import statement called as. Here, if we import supercalifragilisticexpialidocious as sup, then it's importing the module called supercalifragilisticexpialidocious, but rather than assigning it in the local namespace with that name, it's assigning the module object to just the variable sup. So if we try and use sup, then that resolves to the module object, but supercalifragilisticexpialidocious actually doesn't resolve to anything in the local namespace. So it would be an exception to try and use that name. As a similar convenience, sometimes when dealing with modules, we're really just interested in one or two attributes from that module. So there's the from import statement, which imports the specified module just like in a regular import statement, but the module object itself is not actually assigned to any attribute in the local namespace. Rather, just the specified attribute of the module is assigned to the local namespace. So here, for example, from lobster import chicken means we want the attribute chicken from the module lobster. So lobster is imported, but not assigned to the local namespace, but rather chicken is. So we can use chicken directly. We don't have to write lobster.chicken, we can just write chicken. And if we try and use lobster, that's an exception because we didn't actually assign the module into the local namespace. And in a single from import statement, if you want multiple attributes, you just list them separated by commas. So this imports 3 attributes from lobster, chicken, turtle, rabbit, and it assigns all of them directly into the local namespace. And if you want to import an attribute, but not assign it by its given name in the module, but by some alias you choose, you can do so by using from import as. So here this is importing the attribute turtle from the module lobster, but instead of assigning it as the name turtle into the local namespace, it assigns it as t. So t now is a local name referring to the object held in the attribute turtle of the module lobster. Now, a very important thing to keep in mind when using module attributes this way is that when you assign them directly into names of the local namespace, that name is really just an ordinary variable pointing to whatever object was in that attribute at the time of the import. If you then change the attribute of the module, this local reference to it is not automatically going to get updated. So if turtle, say, were some module attribute which you expect to change throughout the course of the program, you wouldn't want to use it via from import. You'd want to always access it as the attribute of the module. You'd want to import the module itself and then always write lobster.turtle to use that value, because that's the only way you get always the most up-to-date value of the module attribute. Finally, there's one more convenience with from import, where maybe you just want to directly import all of the attributes of a module into the local namespace. This is convenient, but it does suffer from the problem I just described, where we're really just creating new local variables that might get out of date with the actual values of the module attribute. It's also generally considered bad practice to use this asterisk, because it means that you're just dumping all the names of some module into your local namespace, and basically polluting your local namespace with a whole bunch of names, many of them which you probably aren't going to use. It also tends to wreak havoc because the module you're importing, someone else or even yourself might modify that module, and that then changes what names get imported, and that can easily cause unexpected name conflicts. And those name conflicts could cause some pretty obnoxious bugs that are hard to track down. You'll be sitting there looking at your code, scratching your head, thinking, hey, I didn't really change anything. Why the hell doesn't this work like it did before? And you'll find out that, oh, well, now there's this name foo in this module which is being imported into the local namespace, thereby obscuring this other foo which I imported from this module just in the line above. So generally I would say just avoid using this asterisk form. I would only use it in an interactive session. The last thing to discuss about imports is what's called a relative import, which is an import that features a dot used to stand alone where the module usually goes in a from import, or the dot is prefixed to the partial name of a package in the same spot in the from import. The idea of a relative import is that we're telling Python where to find our module relative to the current module, the module in which we are using the from import statement. So here, for example, assuming that we're inside a module of the package tiger.whale, well, if you see from.import turtle, that's saying in the package tiger.whale, import the module turtle. And then in the next line, if you see from.eel, import newt, that's saying from tiger.whale.eel, import newt. So in between from and import, we're specifying a relative package, that is a package relative from the current package, and then after import, we're specifying the name of a module in that package. And notice that this is really very different from what a from import normally does. A from import normally is about importing specific attributes from some particular module, whereas here we're importing modules from a particular package. Now, it's possible in these relative imports to use multiple dots, and whereas a single dot is used to signify the current package, 2 dots is used to signify one level up. So in tiger.whale, 2 dots means just the package tiger. So from ... import newt means from tiger import newt in the context of the package tiger.whale. And then from ... eel import newt means from tiger.eel import newt. So again, from tiger.whale we went up one level to tiger, and then we went down to eel inside tiger. So this multiple dots is imitating the syntax you see with file paths, where ... / is used to go up one directory, except here we're not using any slashes. So if you want to go up 2 levels rather than just 1, you write 3 dots. If you want to go up 3 levels, you write 4 dots, and so forth. So the advantages of using relative imports are basically twofold. It makes it easier for you to rename your packages, because when you rename a package directory, you don't have to then go into all the modules of that directory and change all the import statements where one module of the package is using another module of that same package. With relative imports, you don't have to do that, because they're all just referring to other modules of the same package using the dot syntax where the name is left unspecified. Relative imports don't completely solve the problem of package renaming, but they do help a bit.